Hello, my name is Brian Paden. I'm here with CEO and co-founder of Summer Robotics, Skylar Cullen, and we're here to present Kortx, our streaming 3D vision technology. So to motivate what I'll be presenting, let's consider what might be needed for robotic automation solutions to break into new use cases. It goes without saying that there's always a push for more automation to reduce labor costs, but recently there is an increased demand for onshoring manufacturing for more robust supply chains. Furthermore, many tasks that are repetitive and physically demanding can be dangerous and injury-prone, so automation can reduce workplace injuries. In this video, we can see some automotive manufacturing tasks that have not yet been automated. The reason is that the hand-eye coordination and proprioception of a person is still unparalleled by robot technologies. The principal challenges in these use cases are the requirement that parts and fasteners be installed on a moving assembly line whose linear speed is varying and uncertain. Further, the tasks of installing a fastener on a moving assembly requires recognizing and tracking features on the assembly with sufficient speed and accuracy to offset a tool path to the dynamically changing position of the assembly. Before we consider solutions to these challenges, let's look at some examples of the success that automation has had in manufacturing. In this first video, we see an impressive team of ABB robots doing welding manipulation tasks. These robots are highly productive at this task and take humans out of this dangerous work environment. The reason this use case can be automated is that the assemblies come to a stop in fixtures that precisely locate the assembly relative to the robot's base frame, so that the tool path can be executed open loop. In the second video, we see a slightly more sophisticated example of a Delta robot doing a structured pick-and-place task. In this video, a highly customized vision system and motion planning solution is tailored to the use case, and the vision system most likely images the target one time and does not need to dynamically update the motion plan after initially recognizing the target. Recent advancements in AI with GPTs give robots a remarkable capacity to process data and make decisions. I, along with probably many of you, believe that GPT-powered robots will eliminate the elbow grease and software engineering needed to design and deploy customized robot work cells in favor of generalizable robots that can get to work after digesting a worker training manual. However, if we look at one example of a product that has been under development for over 3 years with a virtually unlimited budget, we see that there may be some wrinkles that need to be ironed out. We see a robot executing a pick-and-place task with battery cells. The use case is highly structured, and we can see what looks like a large-scale dataset generation operation specific to this use case. Yet the robot is executing the task slowly and with errors. So what's the limitation here? Why isn't this robot as impressive as the GPT chatbots? Remember that in order to exceed the capabilities of current solutions, we need to see the robot do this task with pretty much just a prompt and not having an army of technicians generating supervised training data. Our thesis is that high-functioning robots are throttled by data that is too high in latency and low in information density to be capable of solving the unmet automation use cases in manufacturing. In particular, conventional camera-based 3D pipelines are a significant bottleneck. Let's look at a rough latency breakdown for generating a stereo depth image with a conventional camera. First, we have to expose the pixels, which can take from 1 millisecond to 50 milliseconds, depending on lighting conditions. Then analog to digital conversion and readout takes 500 microseconds to 2 milliseconds. Next, the transfer to the host processor can take 2.5 milliseconds to 5 milliseconds. Then dense stereo correspondence will take 20 milliseconds to 1 second, depending on compute capabilities. Stereo correspondence also has a significant hardware and electrical cost if using dedicated FPGAs or GPUs. Finally, the 3D depth computation from correspondences can take an additional 2 to 10 milliseconds. In the end, you can expect a conventional pipeline to have a photon to 3D point latency of 25 milliseconds to over a second. You may see frame rates as high as 100 Hz, but this is accomplished through parallel pipelining of sequential readouts, and ultimately the reaction time of a robot will be limited by latency. So we've developed a new 3D vision pipeline designed to enable robot intelligence. This is a new paradigm that prioritizes streaming atomic amounts of data continuously to minimize latency. Our early prototypes have a photon on-chip to 3D data latency of under 5 milliseconds. This video illustrates what the streaming data looks like in ultra slow motion. You can easily recognize the position of the computer mouse after the first pass of the scan without waiting for a full dense reconstruction. The principle of operation is as follows. We rapidly scan a target with a space-filling curve from a laser source. The reflected laser spot is detected by an event sensor or avalanche photodiode array. These sensors differ from conventional cameras in that their readouts are event-triggered instead of time-triggered. So when the laser reflection is incident on a pixel, the pixel immediately reads out the pixel coordinates along with a microsecond resolution timestamp. The correspondence problem in this case is trivial as we match the pixels by their timestamp. This saves a substantial amount of latency, hardware cost, and electrical cost. This feature is key to the differentiation of this technology. The next point I want to highlight is that in robotic applications, a small amount of quality data delivered quickly is superior to a large amount of data delivered with high latency. If we look at 10 milliseconds of integrated scan data on this computer mouse and have a prior on what we are looking for, it's pretty clear where the mouse is in the 3D data. This small amount of data is sufficient for a pick-and-place task. We can also match the behavior of a dense scanner by simply integrating a larger batch of data to obtain a high-resolution reconstruction of the mouse, if a use case calls for it. If we want to compare this sensor to other sensors, we need to be careful about what KPIs we are going to talk about. A key metric marketed for 3D sensors is their throughput in points per second. I will argue that this is a meaningless metric since a points 3D error distribution will vary from sensor to sensor, and even for a given sensor, the error distribution will vary with surface albedo and specularity. Further, the output generated by a sensor's onboard processing may apply smoothing and interpolation to generate a more visually appealing 3D reconstruction and to boost throughput. To illustrate my point, I have our scan of a computer mouse on the left, along with a scan from an Intel RealSense D435 from the same perspective on the right. While the RealSense produces many points per second, you can see the errors are large and have strong spatial correlations between nearby points that suggests smoothing and/or interpolation of sparser data. When considering the trade-offs of different sensors, one may encounter a sensor with less precise measurements but a higher throughput. Remember that throughput is not the same as latency, and averaging a large volume of measurements to reduce an estimator's error variance has diminishing returns. To drive this point home, suppose we are making noisy IID measurements of a variable x and use a sample mean estimator to estimate x. We know that the error distribution's standard deviation is inversely proportional to the square root of the number of measurements, but is directly proportional to the standard deviation of the individual measurements. So there's diminishing return in adding more measurements, but reducing the individual measurements' error variance leads to a proportional reduction in the estimator error variance. Finally, fewer measurements means less bandwidth utilization and lower latency. As presented, this may seem obvious, but it's easy for this point to get lost in marketing specs of various technologies. Another thing to watch out for when evaluating 3D sensor technologies is interpolation and smoothing of raw measurements. Interpolation may increase sample count, and smoothing reduces the standard deviation of measurement errors, but they both introduce strong spatial correlations between nearby measurements that ultimately don't improve an estimator's performance over raw data, which makes sense since the two operations don't add any information content to the data. If we look at the sample mean estimator's error distribution for correlated measurements, we see that the correlation increases the estimator's standard deviation, and in the limit as the correlation coefficient C tends to 1, the estimator is no better than a single measurement. Again, interpolation and smoothing in front of a sophisticated estimation algorithm like a neural network is a waste of bandwidth, memory, and electricity. So how should we compare sensors? I'll argue that a good measure of merit is how much a measurement improves the posterior entropy of a latent variable in bits, normalized by the data bandwidth utilized to communicate the measurement, also in bits. Thus, we have a unitless number of entropy reduction per communication bandwidth. Of course, various other factors are important, such as the price of the sensor, form factor, weight, power consumption, etc. But the information conveyed by a unit of measurement is probably the first and most important consideration. One of the neat features of our technology is that our 3D data stream is free of motion blur. Instead, when we scan an object in motion, we have an invertible motion distortion. Each 3D point has a precise timestamp which we can use to compensate motion-distorted scans given a trajectory in SE3 for the object. we've implemented an efficient real-time motion estimation and compensation functionality that can recover the reconstruction of a moving rigid object as if it were stationary. This is useful in situations where objects are moving quickly and fine details, such as small holes or defects, need to be analyzed. Next, I want to share some applications that are enabled by this technology. This demo shows our tool guidance capability. Our software can receive a part or assembly mesh file via gRPC and then locate the part in the field of view. We then send pose and twist estimates to the robot controller at over 100 Hz to offset the tool path to the part's real-time location. The detection and localization of the target has a photon to pose estimation latency of less than 20 milliseconds, which enables highly dynamic applications. We've also validated the accuracy of the pose estimates to around 100 microns in translation and about 1 arc minute in rotation at a distance of 50 centimeters to 1 meter. Another application we've been working on is inspection of parts and assemblies while in motion. Since we have the motion compensation feature, we can integrate a dense scan of an object in motion and recover the 3D reconstruction as if the part were stationary. This can be used, for example, to detect loose screws or assembly errors. In the graphic shown, we have a photo of a wheel knuckle with a loose screw. We then scan the wheel knuckle and compare the scan to a reference geometry to highlight the discrepancy at the loose screw. To conclude, high latency and low information density data are major bottlenecks in enabling advanced robotic applications. Our technology, Kortx, is a paradigm shift. We focus on streaming atomic 3D data for low latency, high fidelity robot perception. We prioritize noise reduction and over throughput for meaningful data. Some key differentiators of our technology include photon to 3D data latency of less than 5 milliseconds, motion compensation capabilities that enable distortion-free reconstructions of dynamic targets, and accurate tool guidance for dynamic inspection capabilities. This enables robots to perform challenging tasks like dynamic tool guidance on moving assembly lines and precise inspection of fast-moving parts. Looking ahead, we believe this technology will be essential to enabling intelligent robots to interact with the world in real time.